Chapter 5, Computational Algebra, looking at 2x2 linear systems. This will be our introduction to solving simultaneous linear systems. Today we'll be looking at, in addition to what a 2x system is, come back to the concepts of skew targets and mapping the targets, look at the matrix form of how to represent that equation. We'll look at a direct approach using Kramers Rule, go back and look at how we did simultaneous equations and relate that to Gaussian elimination. Look at, within Gaussian elimination, pivoting, and then go talk about the issues of unsolvable or undetermined systems, homogeneous systems. We'll look at a graphical point of view of undoing maps and inverse matrices and look at them from a graphical point of view and defining them, look at the dual view of both of those, and then get back to some terminology you need to make sure you covered it all. So what is a 2x2 linear system? Well, anytime I have two lines, I can think of those as defining a linear system, because I have something like ax equals by equals c equals constant, and I can take two of those and ask the point, where do they intersect? That's one way of looking at what a 2x2 linear system is. And for each of the lines in this drawing here, not all of them, but for any two of them, where they intersect. So if I take this line and this line over here, they intersect at this point here. That's introduction, a system of 2x2 linear equations. Another way of looking at them is in terms of mapping of target boxes in a coordinate system. So if I have some global coordinate system, I want to map it into some possibly distorted, linearly distorted local coordinate system, I can say I'm going to map E1 to A1, E2 to A2, that's straightforward mapping. But now that defines our skew box, I can ask an important question. Given that B is a vector in the E1, E2 coordinate space, what would its representation be in this other space of A1, A2? And we're going to use this example going through here. So if A1 is 2, 1, and A2 is 4, 6, and B is 4, 4, now I can ask the question, how do I represent B, because it's 4, 4 in the E1, E2 system, in the A1, A2 system? And as we go through this, you'll see that it's 1 times A1. If I go over A1, and then I go up here, 1/2 of A2, 1/2 of this vector, I will end up at B. Therefore, the answer is 1 unit of A1 plus 1/2 unit of A2 will be how I represent B. This one I can see that graphically, but we want a more formal, consistent computational approach to solving this. So to do that, we're going to come back and look at it in a slightly different form. So those two equations and two unknowns, I can write two equations. 2u1 plus 4u2 equals 4. u1 plus 6u2 equals 4. And the solution, as we just saw for that, is u equals 1, u equals 2. And there's lots of ways we can solve that. This chapter is going to, in fact, look at many ways we can try and solve that equation. First, we're going to look at how we represent it in what's called matrix form. If I represent it in matrix form, I'm going to take the coefficients of those two equations, line them up so that u1 is always the first variable, u2 is the second variable. And then I get a matrix form of u1, a11 times a11, a12, a21, a22. This is our matrix A times the column vector u1, u2 equals b1, b2. And this is our unknown vector. This is our right-hand side. This is our matrix, and we write that as AU equals B. And in this case, U is called the solution of the linear system. And so the previous example we looked at will be now written in matrix form as 2, 1, 4, 6 times U1, U2 equals 4, 4, and we want to find out what is U1 and U2. Now, looking at that, we can recall the geometric interpretation of of this matrix another way. We can also think that this expresses B as a linear combination of two vectors, A1 and A2. So in this matrix form, this column vector, 2, 1 is A1. This column vector is 4, 6 is U2. Again, if we go back to our graphics, A1 became the first column of our matrix. A2 became the second column of our matrix. So we're asking for that linear combination of the column vectors to represent B. If when we do this, there is at least one solution, the system is called consistent because there's some solution. Otherwise, it's called inconsistent. And there actually turns out to be three possibilities. It's possible there's exactly one vector u, that solves this. There's only one u1, u2, as we had in our example. And that's true when the matrix has full rank and is non-singular. So A is not equals exactly 0. It does, sorry, the determinant of A is not equal to 0, so it has full rank and it's non-singular. There can also be no solution, so it's possible that that'll happen, and there can also be infinitely many solutions. So if the determinant of A is not full, then either of these latter two can come out. And we'll look at those again later. But first, let's go back to how do we solve this in general cases. So the first is a direct approach called Kramers Rule. And we can think of this one sort of geometrically. And this is based on the concept of the ratio of areas. So if I think of this parallelogram going from the origin to A2 and from the origin to B up to here, right? So this parallelogram. And we're going to look at the area of that parallelogram divided by the overall area of A1, A2. So what we're looking at is this parallelogram divided by this parallelogram's area, and that gives us a factor really that'll tell us what is the solution for U1, because U1 is the fraction we move in the A1 direction, and you can sort of see that this area divided by that area is that scaled vection. It's the projection down to this direction for that area. That's the shear parallelogram, and for U2 we do something similar. We look at A1, B1, the parallelogram, divided by the area of A1, A2. And since shearing preserves areas, right, that gives us a formula then for U1, U2, and that gives us a direct way of looking at that. Now, we know, now this is straightforward if you're good at computing the areas, but it turns out, going back to our definition of the determinant, we can actually compute this pretty easily because the determinant of this parallelogram is really just, sorry, the area of this parallelogram is just given by the determinant of the associated matrix. So if I want to ask for the area of BA2, I just build a vector of B, 4, 4, A2, 4, 6. Remember, here's B, here's A2. Take the determinant of that, which is 4 times 6 minus 4 times 4, which is 8. The determinant on the bottom is A1, A2. A1, A2, the determinant of that is 8. So I get U1 is 8 over 8. U2, I take the determinant of A1 and B and the determinant of A1, A2, and I get 4 over 8. So that tells me that U1 equals 1, U2 equals 1/2, which we've already seen works out to be the right answer. But this also shows you some problems. What happens if the tops are 0? That's not a problem. If the determinant of B and of A2 is 0, then this will just be 0 on top. But if the bottom, if the determinant of the matrix is 0, then we'll have something divided by 0, which is not a valid number, and we have to then say this one is inconsistent. So it turns out that Kramers rule is nice theoretically, you can sometimes use it, but for larger systems it's very expensive and it's numerically unstable, so it will cause us problems computationally. So before we get to the computational way of looking at it, I want to go back to high school and talk about how you probably solve simultaneous equations back then, using what you would have called substitution. So the first step is to solve one equation for one variable. So if I have something in terms of y and a, I go out and solve for one variable. And then I'm going to substitute that back into the other equation. I'm going to simplify and solve that equation. So now I'll get an answer for the variable that's left. And I'm going to substitute that back into the original equation to find the value of the first variable that I got rid of. And then I'm going to check the solution in both equations. So I'll go through 2 examples, and that'll actually help motivate where we're going to go in a second. So if I take this equation, I have minus 4x plus y equals 0, 3x plus y equals minus 21. Well, the first of these is trivially solved, so I just get y equals 4x. And I can substitute that into the other expression, so I just replace y with 4x. I can simplify that and solve, so I get 7x minus 21, so x is minus 3. Now I'm going to take that, I'm going to substitute back into the original equation, so I'm going to take 3x plus y minus 21, stick in minus 3 for x, solve, simplify that, solve, I get y equals minus 12. So that tells me that overall my solution is minus 3 for the first element, minus 12. Okay, now I'm going to go back and check, just stick in minus 3 and 12, minus 3 and 12, and yes, I get minus 12 is 12, so I checked. Check the second equation, make sure we didn't have any errors. So we put in minus 3 and 12, check the math, we get minus 21. Always good to check when you're doing it this way. So a second set of equations, here I have x plus y equals minus 10, 5x minus y equals 2. If I go to solve for one equation, one variable, this time it's a little bit more complicated. Y equals minus x plus 10, so I have this extra variable constant I have to carry around. I'm going to substitute that in, so I'm going to take 5x minus y equals 2, put in minus x plus 10 for y, so I'm going to simplify that out, and I get 6x equals 12, so x equals 2. Now I can substitute that back in to find the original variable. So put in 2 for x, so y equals 8, and the overall solution to this is 2, 8. Once again, a quick check, put it back in, and I get that it checks out in both equations. So now, this is a way we learned all this in high school, and given any 2x2 equation, you can sort of plug through this and make it work. This gets to be tedious and impractical when the number of equations gets larger. So it's interesting to ask if there's a better way of looking at this. And this, if you think about these two equations, the first one was a little bit easier because one of the two variables sort of easily went away. So what would that look like? So if I have an equation that doesn't have a variable, that equation is much simpler. So imagine I have this special case of a matrix that looks like A1, 0, A1, 2, 2, 2, B, right? So this one, if I go to solve for U2, it's trivial. It's just B2 divided by A2 because this direction, right, is already there. All I have to do is say, well, what's the component upward? It's just U2 is just B2 divided by A2, and that'll give me this height. And then I can substitute that back in. So this upper triangular form is called upper triangular because everything above the diagonal, this forms a little triangle up here, and this is 0. It's trivially solved with a process called back substitution. So, nice property. Now the question is, how can we get there? So if we start with a general solution, turns out we can get there by using what's called forward elimination. The process of forward elimination followed by back substitution is combined called Gaussian elimination. So if we go back to our general equation, how are we going to get there? Well, notice that if I go back to this graphic of the special case has this column A1, 1, 0, right? So this column is already on the E1 axis. So we can ask the question, given a general equation, how can I push it down to be on the axis? How do you move everything down? Well, we can do that with a shear transformation. And an important, very important fact for this chapter, you have to remember this, it will be on quizzes, midterms, or exams, is that linear maps don't change the linear combination. So if I were to multiply both sides of this matrix by both sides by a matrix, so if I want to go from here to here, and I multiply both sides, I'm not going to change my solution. So if I take some matrix S, and I multiply it by this on both sides, and if S is non-singular, it's important that S is a full rank, then this is a perfectly valid set of equations, and it doesn't change because I multiply both sides. If you think back to regular algebra, this is just like multiplying both sides of an equation by a constant. As long as that constant is not 0, the equation is still true. So I can now ask, what is S that lets me solve for this? I want to skew this down so that I'm on this axis. Then I know I can do the upper triangular, and I can do that. So to do that, I want to decide that I want to map 2, 1, which is where A1 is, down to 2, 0. So what's the skew matrix that will do that? Well, if you can remember the formula, or if you just derive it, the skew matrix S1, which is 1 minus 1/2, 0, 1, will do that. It'll map it, the A down on the E2 axis, or A down to the E1 axis, and leave the E2 axis alone. So it'll skew everything there. So now, given we've done that, we can multiply our original equation, and I can take that times the first element of my matrix, the second element of my matrix on the right-hand side, so I end up with a new system of equations. After I've done those transformations, I have 2, 0, 4, 4, 4, 2, because I've transformed this column vector, this column vector, this column vector. So I can look at that matrix form as 2, 0, 4, 4 times U1, U2 equals 4, 2. Whatever U1, U2 solves this, solves the original equation. I can now put that back in back substitution, solve for U2, because I just take 2 divided by 4, and then I put that back in and I solve for U1 equals 1. So this gives me back my solution. So the nice part about that is it's a procedure. I can follow it. But there is a problem. What happens in an example where I want to shear it and I really can't? Shearing A1 onto the x2 axis will not work, because if I want to shear A1 onto this axis, it'll become the point 0, which is not good. Now I won't be able to solve everything. So what happens if this diagonal element, which we called before, remember we called the diagonals pivots, if that is 0, then I can't do my shearing. So what we're going to do is exchange the two equations. We're going to just take the two rows and flip them, okay? And exchanging two rows, so the pivot in the largest absolute value is called row or partial pivoting, and we can do this to improve the numeric stability. So if it's 0, we have no choice. But what happens if the matrix we had was 0.000111, U12, whatever. If I go to shear that, I'm going to matrix that's going to have 0.0001 here, but 9999 here, and that's a big number. And if I do this correctly, I'll probably, if I have enough digits, I can make it work. If I do back substitution, I'm going to get an answer. But if I only kept track of 3 decimal digits, I'm going to get a very wrong answer. And this is the idea of what we consider round-off error, which we'll talk about a lot more. So our goal in pivoting is to dampen that effect. If I were to take that same matrix and I'm going to pivot it so that the first row becomes the top, then when I go to solve this, I get a very good answer in terms of where I want to go in terms of the answer. So it's much closer to the true solution. So this idea of pivoting is whenever the diagonal is a bad number compared to the other numbers, we're going to swap them. So what's swapping? Again, swapping is really multiplying by both sides of the equations by a special matrix that's going to swap the top and the bottom. Okay, so we're going to use an interchange matrix. Okay, so now we've talked about the basics of Gaussian elimination. We have to talk a little bit about what happens when things go bad. When they go really bad and we can't pivot, it's possible to have a system that looks like this. In this case, A1 and A2 are linearly dependent. So we have something like 4, 2, 1, 2, U1 equals 1, 0. And if I go to do forward elimination, if I want to shear A1 onto this axis, when I do that, because these are parallel, I will also be shearing A2 onto this axis, and I'll get an equation that looks like 2U1 plus 1U2 equals 1, and 0 times each of these equals minus 1. That last equation of 0 equals minus 1 is not valid, so this system is inconsistent. There is no solution that will satisfy this equation. And it's actually sort of easy to see that graphically as well. If I take any linear combination of these two vectors, I will stay on this line forever. No combination of those vectors can give me B, which is not on that line. It also gives you an idea why we can have an underdetermined system. If I have all 3 of A1, A2, and B all on the same line, so they're all parallel, then when I go to shear it down, the last equation, 0 equals 0, will be true always. It's sort of trivial. So this is really one equation in 2 unknowns. And one equation in 2 unknowns is underdetermined, and it has at least one solution. I can put any value I want in, but for any value of U1, any value of U2, there'll always be a value of U1 that works. So there's infinitely many solutions, actually, not just one. So a special kind of matrix occurs when we use a special value of B, which we call a homogeneous solution, or a homogeneous system. In a homogeneous system, we ask, what linear combination of vectors lets us equal the 0 vector? Okay, there's clearly a trivial solution if I just let the vector u equal 0. And usually this is not particularly interesting. So what we really want to ask the question is, if there's a solution that's not equal to 0, okay, if there is, then all scalar multiples of that exist, and there must be an infinite number of solutions. So in this case, I have 2 dependent vectors, A1 and A2, okay, and this value of u will allow us to say A, which is the A1, A2, right? That's our matrix, times u equals 0. That gives us an infinite number of solutions if u was pointing in the same direction as A1 and A2. The example we actually just saw here would have that property. But if u is, in general, if A1 and A2 are not in the same, right, then we won't have a solution. Not all homogeneous solutions have a non-trivial solution. So only rank 1 maps for a 2 by 2 matrix. So in general, only only degenerate rank maps will have, that are linearly dependent will have a non-trivial solution. So another way of looking at is the system solvable is to ask, is the homogeneous solution solvable? If the only trivial solution is 0, if the homogeneous solution is only solvable with a trivial u equals 0, then A is an invertible matrix. And you can sort of see that graphically by thinking, if I have some general u, not a point on the origin, but any other point for u, then I must have taken some linear combination of these vectors and not reached the origin. So I will have, these two vectors must be parallel. Otherwise, the only way to make them cancel out is to have the trivial solution. So if we go back to the inhomogeneous example, the homogeneous example we looked before with 1, 2, 2, 4, which we know are dependent, equals 0, 0. If I go to shear this again by doing the forward elimination, I'm going to get 1, 0, 2, 0, u equals 0, 0. If I pick u2 equals 1 and then do back substitution, I'm going to get u1 equals minus 2. Now this turns out to be a special case because any cu that is perpendicular to a1 is a solution. So if I take any other constant times a1 dotted with u, right, this is perpendicular to anything that's on this line. So u now, in this case, because it's the solution, the non-trivial solution for the homogeneous equation, the homogeneous system, we call this the kernel or the null space of A. And we'll talk a lot more about that when we get to higher dimensions. Because this is the only trivial solution, if we go back to another matrix where there's only one trivial solution, there's only the trivial solution exists. We're going to take 2, 1, u2. When we go to shear this, we're going to get a perfectly valid 1, 0, 2 minus 3 matrix equals 0. The only solution to this equation is 0. So we now have a solution where we know this matrix is invertible. Now, we introduced the idea before of a homogeneous, of pivoting. And when we introduced it, we used the trivial solution, what's called row pivoting. But sometimes we have a solution where I can't even solve it with row pivoting because everything in this column is 0. So if I go to do everything in this column is 0, nothing I swap will let me to do a shear in the E1 direction. I have to shear the other direction, which is equivalent to doing what's called column pivoting, which is exchanging rows, and exchanging columns. Notice that when we exchange rows, I left the variables alone, but if I exchange columns, I have to swap the variables because I need to say it's always going to have to be 1/2 times u2, because here it was 1/2 times u2. So I exchange the variables, now I solve it, now I can do this, and in this equation I'm going to get u1 equals 1, and substitute that back in, and I'll get the null space is 1, 0, and that gives me a solution. Now notice, in fact, I only have to do column pivoting if the matrix is singular, because that's the only way to have all zeros in a column. And if there's a column of all zeros, we already know they're linearly dependent, but if I want to figure out what is the null space, it may still be useful to do that. Okay, so now if we're going to put all this together, there's some other ways we can look at this. So Gaussian elimination is a very important part, but if I want to think about maps in general, I want to think about what does it mean to solve an equation. So if we think about undoing a linear map, so if I'm given some map AU equals B, we can think of that as mapping U onto B if I'm given U. Or if I'm given B, I'm asking what's the U that I can map. Okay, so you can ask the question, what is the matrix B that maps B back to U? So I can look at this as U is equal to some matrix B times B. Okay, this B is called the inverse map. And just as we did during Gaussian eliminations, we can use shears to make this sort of interesting. So if I go back to the original matrix equation, and I think about the shear I used for Gaussian elimination, I'm going to shear that down, and I'll get this. So now I have a new matrix equation. I've applied S1 on both sides. Now, in this case, I'm going to do a second shear. I'm going to multiply both sides by a second shear. And this second shear, I'm going to map on the E2 axis. and I'm going to get this matrix, 2, 0, 0, 4. So now I've sheared left, or sheared down, now I'm going to shear left. I get a new matrix, and now I can apply some scaling, non-uniform scaling in this case. I'm going to do 1/2 and 1/4, and 1/2 and 1/4 will make this go to the identity matrix, and the right-hand side will now be reduced to 1 and 1/2. So another way of looking at this process we did in Gauss elimination is actually that we're going to reduce this to the left-hand side is going to be reduced to the identity matrix, and the right-hand side will give us the answer. But if I put all that together, I also have multiplied both sides by the concatenation of the matrix S1, then that was multiplied by S2, which was multiplied by S3. If we put that all together, we can call that matrix A inverse, which is what we call the inverse of a matrix. I is the identity matrix. And A is called invertible if this matrix exists. If doing this, I can't actually do some operation. So if one of these scales was not definable because, say, this column was 0, then I couldn't take 1/0. That would be nonsense. So then I would not be able to compute A. But if I go through this process of doing each of these shears and scaling, and in 2 by 2 it's always 2 shears and the scaling will be sufficient, then I can find the invertible matrix. Okay? So now algebraically that's given us one way of looking at an inverse. We can also think about it a little bit graphically. So the inverse has some very important properties, because if I think about what it's going to do, if I take the inverse times the matrix, I get the identity. In fact, you can sort of see that this inverse, right? This inverse is S3, S2, S1. S3, S2, S1 times A equals the identity. So we get that directly from that equation. With a little bit more work, you can see that A times A inverse is equal to the identity, and the identity is its own identity, or it's its own inverse. So the inverse of a scaling turns out to be very simple. If I have a scaling matrix with S and T for the two axes I want to scale, then the inverse of that is just 1/S, 1/T on the diagonal. And that's pretty easy. You can see if you multiply these out, you're going to get 1/S times S, 1/T times T, and as long as T and S are not 0, that'll work out. Graphically, that's sort of going from our phoenix, which is circular-ish, to this ellipsal object. The inverse of this ellipsal object goes back to this. So if I scale it down and then scale it back up in the horizontal axis, I will get the nice shape. Conversely, if I were to scale it up by the inverse of the matrix and then scale it back down, I get the same thing. So I see these graphically. Again, if you think of maps in terms of how they operate on the circle, you get the action ellipse and can sort of visualize what's going on. They don't even have to be, of course, just scale matrices. We can talk about a shear, so I can shear everything along the horizontal axis, and then the inverse turns out to just be one of the shear factor, and I shear it back, and I can do that for either axis. Okay, although here these are both the original shape sheared and back, the original shape sheared a different way, with the inverse shear and then back. And so this shear moves things to the left, this shear moves things to the right, and if you go left and then right, you're back where you started by the same amounts. Rotation matrices have another special property, but it's not quite as simple. So if I think about rotating by theta, well, if I want to rotate by minus theta, that would be the inverse. So if I go rotate by theta, rotate by minus theta, I'll be back where I started. And it turns out that because of the properties of sines and cosines, if you look at the transpose of the rotation matrix by alpha, it is the inverse. So a rotation matrix also has a special name. It's a type of orthogonal matrix, and that's true for any matrix whose transpose equals its inverse. Okay, all rotations are orthogonal, but not all orthogonal transformations are matrices. Or rotation matrices. Okay, if an orthogonal matrix has the special property, an orthonormal matrix has a special property that the length of all of its columns are 0, and the the length of each of its columns is 1, and the dot product of its columns are 0. Okay, these vectors are called orthonormal. Normal because they equal 1, ortho because they're orthogonal, which means their dot product is 0. Any map that has these properties is a rigid body motion overall, and it's characterized by having a determinant of plus or minus 1. So again, if we look at these graphically a little bit, going back to our inverse matrices. So here, if I have a more complicated map, the inverse of the inverse is the original matrix. The inverse transpose is the transpose's inverse. So in the top here, I have something that's not a trivial transform. So here I'm going to have the inverse of a map, and then its transpose. Here we have the transpose of the map, followed by its inverse. And we still end up with the same shapes. So how to compute A's inverse? Well, if we start by thinking of this as AA inverse equals the identity matrix, we denote two unknown columns by A1 and A2. So we're going to denote the columns of I by E1, E2. So if I start by setting up the equation A times this matrix equals that matrix, it's really shorthand for two linear systems. A times A1 equals E1 and A times E2 equals E2. Both of these matrices have the same matrix A, so I can really work on either one. And so I can just take this vector, try and solve it. That'll give me A's inverse. If I solve both of them, I get the two columns of A1 and A2. Now I have the columns that make up the inverse. So we actually have two different ways to solve for the inverse. One, as you saw, we set up the equations and we reduced the left-hand side of the identity, and by following through on all those sets, the right-hand side now gave us the inverse. Or we can just set up multiple equations and solve each of those equations using whatever method we want. Okay. So now we've been talking about these as maps. Let's be a little more formal what we're going to do with this. Matrices map vectors to vectors. And so if V1 is mapped to V2 and V1 prime to V2 prime, sorry, if V1 and V2 are mapped to V1 prime and V2 prime, what matrix did it? So we have some matrix A that's going to map V1 to V1 prime and V2 to V2 prime. If we combine these into a system of equations, we actually have a matrix times a matrix equals a matrix. So there's some AV equals V prime. So if I can find V inverse, then I can say that the matrix A I want is V prime V inverse. Why? Because I can put V inverse here and V inverse here. This will now become the identity, and this will become the identity if I put V inverse times V, and I'll get V prime V inverse. So I have to right multiply. It's very important when we multiply both sides of an equation with matrices that if I put them in the front, I put them on the front and both sides. If I put them on the back, or post-multiply, I put them on the back and both sides. And that's because matrices, remember, don't commute. I can't rearrange them for multiplication. So in this case, V1 and V2 must be linearly independent so that this has an inverse. And if they are linearly independent, then the matrix A represents a change of basis. So this is a formal set of maps. Other things are degenerate maps and we might not want to use them. So given a problem where you're given, I want to map two vectors to two other vectors, you want to find the matrix A that did it, you represent it as a matrix times matrix equation, find an inverse, and it'll give you a solution. So to think of a change of basis examples, let's say I want to map V1, V2 into V1 prime, V2 prime. Now, graphically, you can sort of look at this one and think, oh, look, this is a rotation by 180 degrees. But if I just give you the vectors, you may or may not be able to recognize that. So just do it algebraically. We have V1 is 1, 1, V2 is minus 1, 1, V1 prime is minus 1, minus 1, V2 is 1, minus 1. This gives us the matrix for V, that gives us a matrix for V, right? For V from the top two, for V prime. And now I can talk about what is V inverse. V inverse is 1/2, minus 1/2, 1/2, 1/2. Again, we're not going to go through all deriving that, but I put all those two together, and I'm going to get that V prime times V inverse is minus 1, minus 1, which is minus 180 degree rotation matrices. So once you know how to find an inverse with these matrices, it's pretty easy to now solve this kind of equation by putting these all together. Okay. So we've talked here, and we actually talked a couple of times about representations. And so it's important that we finally end this chapter by looking at what we call the dual view. So for any linear system, there's actually two interpretations. So if we view what we call the column view, it's a coordinate system or linear combination approach. So this is transforming from one space to another, where the columns are telling us what's going on in the transformation. Another way we can look at it is what we call the row view, which is focusing on the row equations and is like the line intersection. As we started the chapter, we looked at it that way. So the line intersection problem can provide examples for both of these. If I have a parametric and a parametric line, then I'm really looking at it from a column view, where if I have an implicit line and implicit line, where I have equations that look like something times x plus something times y equals 0, or equals some right-hand side, then I'm looking at the row view. And so implicit lines are the row view, parametric view are the line view, and you can really choose the best thing that. So we can also look graphically at some of the other stuff we saw in this chapter. If we think about the linear systems we have, if I look at them from an equation point of view, if I have a unique solution, then I have two lines that intersect. If I have an inconsistent solution, what I have is two lines that are parallel but don't touch each other. Therefore, I can't find a point of intersection. In an underdetermined system where I have infinitely many solutions, the two lines lie on top of each other. So by looking at them, we can also sort of see that here I have two columns that are linearly independent. Here I have two columns that are linearly dependent, but the right-hand side is different. And here I have two, is inconsistent. And then here I have two equations that are linearly dependent, and the right-hand side is actually the same linearly dependent. So as you get to the end of the chapter, make sure you look at some of the questions at the end of the chapter. For example, how to use Kramers Rule to solve a solution, how to use Gaussian elimination to solve a solution, where you have to think about what are the shears you're going to do, Gaussian elimination with pivoting, where you have to do some pivots. We didn't derive a pivot matrix, but you might be able to do that, or need to be able to do that. Answer questions like, what's the null space of this matrix? What's the inverse of any matrix, especially the simple ones like a scaling matrix or a rotation matrix or a skew matrix. Be able to answer questions like, define the matrix A that maps this and 0204 or 2004 to 11 minus 11. Any two numbers, you should be able to do that. We introduced a lot of terminology in this chapter. A lot of this is very important for overall linear systems, so you should know all of the terms that show up at the end of the chapter. The kernel and null space, the homogeneous, back substitution, what's orthogonal. So a lot of terminology that can be easy questions for multiple choice questions or just definitions on a closed book part of the exam.